Hi everyone. So in this video I'll try to explain the simplex method. So simplex method is a method to solve linear programming problem. So what do we understand by a linear programming problem? Now the objective function has to be linear, that is of the form of C transpose X, where C is the coefficient vector. What can be an example? Like z equals to 2x plus 3y, or in terms of x, if we want to write 2x1 plus 3x2. So this can either be a minimization or a maximization problem. But for simplex cases we will try to consider the minimization case only, because this is essential for the simplex algorithm to work. So an easy way to do so, whenever you have, let's say, maximize z, so you can convert it into minimization of minus z, subject to the same constraints. Now let's talk about constraints. Since it is a linear programming problem, so the constraints also has to be linear, and this can be of three types: greater than or equals to, greater than or equals to, less than or equals to, and equals to. Let's take an example of each of these three. For a two variable problem, let's say you have 2x1 plus 3x2 less than equals to 5, 7x2 plus, let's say, 5x1 greater than equals to 2, and x1 plus x2 equals to 5. So these are the three type of constraints that we have. So now let's start with the simplex method. So what is the requirements? First, clearly it has to be an LPP, linear programming problem. Second, objective has to be of minimization. Objective has to be minimization. Then third, all the constraints must be of the form Ax equals to b, where b is greater than or equals to 0. Now let us expand on this. What do you mean by Ax equals to b? For the case 1, if we have greater than or equals to, so this becomes a, the first row xj is greater than or equals to b1. So let's say the first constraint is a greater than or equals to type. So now what happens? This has to be converted into an equality constraint by using a surplus and an artificial variable. Also, one more thing, all the x has to be also greater than or equals to 0. Sorry for that. Now surplus variables are those which can actually be used in a less than equals to type or a greater than equals to type constraints, so that we can convert an inequality to an inequality constraints. So suppose we have a less than equal to constraint like 2x1 plus x2 less than equals to 5. So using a surplus variable x3, we can write 2x1 plus x2 plus x3 equals to 5, where x3 is greater than or equals to 0. Now what happens with artificial variables? Since we have a greater than equals to constraint, let's take the same constraint but with a greater than equals to sign. So now either we can do 2x1 plus x2 minus x3 equals to 5, where this will be a surplus variable. But what happens? This minus 1 coefficient will create a problem while using the simplex algorithm. So what we do, not using this, but we take one more variable that will be an artificial variable, x4. So we write it as x1 plus x2 minus x3 plus x4 equals to 5, where x3 x4 is greater than equals to 0. So this is the algorithmic strategy that we use to convert inequality constraints to equality constraints. So we'll get this type of relation, and we have to be very careful that all the b's on the right hand side has to be greater than or equals to 0. If by some way it is coming out to be less than or equals to 0, we can multiply with -1 on both the sides and change the sign of b accordingly. So now some basic features of simplex. Basic features of simplex. We start with some C transpose x and constraints ax equals to b with b greater than equals to 0 and x greater than equals to 0. So now what happens? We want to minimize this, suppose. Now we need to introduce surplus and slack variables. Slack or artificial, they mean the same thing. Now all these together will convert the inequality constraints to this form. And now your x, whatever initially it was, let's take a example. Let's say we have 2x1 plus 3x2 subject to x1 x2 less than 2, 2x1 plus 3x2 greater than equals to 3, with x1 x2 greater than 0. So to convert it into equality constraints, we use the surplus and the slack variables. So this becomes x1 plus x2 plus x3 equals to 2, and 2x1 plus 3x2 minus x4 plus x5 equals to 3. Here this is the artificial variable, and x3 and x4 are slack variables, so surplus variables. So now what happens? We add them here. So surplus variables are added with a coefficient 0, so 0 times x3 plus 0 times x4, and the artificial variable is added with a very big quantity, let us say m x5. So these are the additional terms that we add after converting inequality to equality constraints. So in order to remove this m from the equation, because we want to minimize z, so we don't want m to be here, so we use two-phase simplex method. In which what we do, we try to eliminate m. So all these will be explained by examples in the later videos. Now some consequences. So what are the possible solutions that we can get to an LPP using simplex? The outcomes: you can get a optimal solution, and you can get unboundedness, and you can get an infeasible solution. So we will see each of them in a separate video. Okay, thank you.